Hello everybody. Let's take a look at the solutions for topic 10.1. My methodology may be a little bit different from your book in some cases, or it may be the same. Let's get into it. First, we're asked to calculate the difference in potential energy of a satellite of mass 1,500 kilograms when it's taken from the surface of the Earth. We're given the radius of the Earth, and we're given a distance of 520 kilometers above the Earth's surface. So I have a small r there as our radius above the Earth's surface, and everything else we kind of will define here as we go along. Okay, so change in potential energy will be given by final potential energy minus initial potential energy, which I have called E sub 1 here, and E sub 0 respectively. Okay, we then plug in this formula. Quick note, fun note, this is not in your data booklet. And actually, wait a minute, wait. No, I take it back, it is. It's just under topic 10.2. Okay, that is good. That is very, very good, because otherwise you would need to memorize this. Okay, moving along here, we can see that my equation simplifies down to this. It's not really simplifying much, but that big R there is the radius of the Earth. The little r is the radius or distance above the Earth, okay? So this part here is an important step where we add those two distances together. Okay, we then have to do some rather annoying algebra, or not. Plugging this into your calculator is not trivial, so you might consider calculating each of these values separately. In fact, that would probably be a good idea on your exam anyway, and it'll simplify your final calculation. Just for the sake of saving some space, I've done the entire calculation all at once, but you don't have to do this. And in fact, there may be some advantages to not doing your calculation all at once. So don't feel obligated to do it just because I did it that way. We could just calculate these two values separately and then put them all together. Okay, so we get this answer, 7.06 times 10 to the 9 joules. Is our change in potential energy. And I've asked here, what about MGH? We have been told previously that that is how you calculate gravitational potential energy, right? So let's try it. We plug in our values, including our change in height, which is 520 kilometers above the Earth's surface. And we get this value, 7.65 times 10 to the 9 joules. Now, this is close to our answer, but not close enough. It's too big. And the reason for that is because the value of G is getting smaller as we get further away from the Earth. 520 kilograms is a considerable distance, and it's big enough that our approximation, as given by MGH, is no longer good enough. Normally, this would be fine for short changes in height, small changes in height, but we don't have those with 520 kilometers. Okay, for 10.2, we're asked to calculate the gravitational potential energy, gravitational potential, not energy, at point P. So, luckily here, we do not have to deal with vectors, which is quite nice. Remember that our gravitational potential is simply the sum of the gravitational potentials at that point, okay? So our total gravitational potential is just given by this equation, where we have the gravitational potential from the first body plus the gravitational potential of the second body. And you can see, once again, I've kind of combined all the math, but if you wanted to calculate these separately, that's not a bad idea, and it's going to simplify what you plug into your calculator. Again, just for the sake of space, I have a tendency to do it all at once, but you don't have to. Okay, when we plug in all our values into the formula that we've calculated using algebra, we will find that our total gravitational potential is negative 8.59 times 10 to the negative 4 joules per kilogram. Do pay attention to that unit. It can help you if you want to do some dimensional analysis to kind of check your final answer. Okay, all right, so let's take a look at 10.3. This one is, I would not say terribly complicated, but if you haven't set it up before, you may have found this one a little tricky. So, when in doubt, draw yourself a diagram, okay? First, let's set up the problem. The mass of the moon is about 81 times smaller than that of the Earth. The distance between the Earth and the moon is given, and the mass of the Earth is also given. So we are asked to find the distance from the center of the Earth to a point where the combined gravitational field is 0, okay, from both bodies. So here again, when in doubt, draw a diagram. In case it's not entirely clear here, this is the Earth, and this is the moon. There we go. Okay, so to point P, we have this distance r sub e, and we have this distance r sub m, and that is the distance from the moon to point P. The total distance between the Earth and the moon will be given by d, which of course is then a sum of r sub e and r sub m, okay? So at point P, we can easily say that r sub e is going to be the distance between the two bodies minus r sub m. Now this is how I set it up, and this was not a fantastic move because this will set me up to solve for the distance to the moon. It's fine, we can still use it, but it would be slightly faster to solve for the moon, the distance to the moon in terms of the distance to the Earth. And you'll see why here in a second. Okay, once we have determined what our radii are going to look like, we'll have this equation here. So we know that gravitational field strength is given by the universal gravitational constant times the mass of a body divided by radius squared. And we know that at point P, our total gravitational field strength should be 0. So what that gives us is this. The sum of these two things would be 0. So that means that they are equal to each other. We have here on the left the gravitational field strength of the Earth, and on the right we have the gravitational field strength of the moon. Okay, I then substitute the mass of the moon with its value in terms of the mass of the Earth, where it is 81 times smaller than the mass of the Earth. So we plug that in. What we find then next is that the gravitational constant and the mass of the Earth will cancel out. And with a little more algebra, we get to 81 times the radius between the moon and point P squared equal to the quantity d minus r sub m squared. And this is very, very convenient now because we can take the square root of all of our terms, and we don't have to worry about quadratic formulae or other such useful but kind of annoying math tools. And we get r sub m here in terms of d, and we'll find that the distance to the moon from point P is equal to 1/10 the total distance between the Earth and the moon, which is given by 3.8 times 10 to the 7 meters. Now, to calculate then the distance from the Earth to point P, we need to subtract that value from the entire distance between the two bodies, And that will give us the distance from the Earth to point P as 3.4 times 10 to the 8th meters. Okay? Yes. All right. I split this up because this part took quite a lot of space. So for part B, we're asked to find the combined gravitational potential at that point. And as we saw previously, our gravitational potential is just going to be the sum of our two gravitational potentials from each body. Okay? So actually, we need this distance to the moon, which is convenient because we've already calculated it using my method. Your book just goes straight for the distance from the Earth to point P, which is fine. It doesn't matter. All right. So once again, we can do a little bit of algebraic simplification here, and I've done that so I can plug it all into my calculator at once. Again, don't be shy about just calculating each of these values separately, and I would probably do that on exams. However, I do like doing algebra, as you can see. So anyway, I do my algebra and I get negative 1.3 times 10 to the 6 joules per kilogram. Finally, for point C, calculate the potential energy of a probe at that point. Finally, something really quite easy. We just take the formula in the data booklet under some subtopic 10.1 and we plug in our mass value and multiply it by the gravitational potential that we calculated previously. And we get 3.24 times 10 to the 9 joules. Okay. 10.4, they start us off with a mistake, which is always awesome. So let's take a look. This radius here should be 2 times 10 to the negative 9 meters. It's not necessarily obvious that that would be the case, but a pretty good indicator is the fact that they've drawn this dotted line on the graph for us. And the only possible value for that line at 2 is 2 times 10 to the 6 meters, not 10 to the 9 meters. So basically, we just find our values for our gravitational potential from the chart. We're given this value, 7.5 times 10 to the 6 meters. So we looked that up on our chart, and we find that the gravitational potential at that point is negative 7 times 10 to the 9 joules per kilogram. We then look up, so that's going to give our final gravitational potential. Our initial gravitational potential, as I said before, is already kind of indicated on the chart by this 2, and we follow that down and we find that we get negative 26 times 10 to the 9 joules per kilogram. We can then plug those values into our formula directly. Your book has split this into 2 steps as well, where they calculate the the change in gravitational potential. You can do it separately or you can do it all at once. It's probably a bit faster in this case to do it all at once. So there you go. 6.5 times 10 to the 13 joules will be the correct answer. 10.5, fairly straightforward. However, so find the electric potential a distance of 0.5 times 10 to the negative 10 meters from the proton of the hydrogen atom. The proton has a charge of 1.6 times 10 to the negative 19 coulombs, equal and opposite to that of the coulomb. Okay, so we plug in our values, and what we find is we have 29 joules per coulomb. Note our unit here for electric potential is in fact volts, which is also the unit for potential difference. Just let that sink in for a second. Okay, so you're right now uncovering secrets of the universe. It's pretty cool. All right, so we have 29 volts as our electric potential at that point in space. Okay. Part B, use your answer to A to calculate the electric potential energy between the proton and a hydrogen atom and an electron orbiting the proton at the same radius. And here, very straightforward, we just multiply the fundamental charge. For an electron, this value is negative, and that negative sign is important. We're not looking at the magnitude of charge here. Okay, so we will find then that our work is negative 4.6 times 10 to the negative 18 joules. And I believe, oh no, we have one more. Okay. 10.16 gives us two unequal positive charges, plus Q, plus large Q, and plus small q. Which one of the graphs below shows the variation with distance x from the larger charge of the electric potential V sub E along the line joining the centers of the charges? Okay, so basically, as we move here from charge Q over to, charge plus large Q over to plus small q, what we're going to find is that initially we have a decrease, but as we get closer to our other charge, it's going to increase. Okay, so this should be pretty apparent right away. And when we look at our possible answers, what you'll find is that every single one of these has that relationship. Okay, so we need to get a little more detailed here. So first, let's just recognize what's going on here. We have two potentials, and each of those potentials is given by Coulomb's constant times the charge divided by the distance from each charge. Okay, so we know that the big Q has a larger charge than the smaller q. Okay, so we need to think about what that looks like. And on each of these, I have eliminated an answer just based on some problems. A and B are pretty close, but B is the better answer of the two because answer A, our lines, our graph is just too symmetrical, okay? It looks more like a bowl, and that's not what we need here. What we need here is a distinctive shift in that dip, particularly this dip here, okay? And what you can see here is we can see both of our functions have a clear shape, because remember that this graph is the sum essentially of two different functions. Okay, so we have the slope here for one of our functions, and we have the slope for the other function, Coulomb's constant times big Q divided by the distance from big Q, and that is going to give kind of a more extreme, less extreme, change in slope as opposed to our smaller charge. Okay, so why not this too symmetrical? Why not this? Because this one implies that small q is bigger than large q, and that is not the case. Why not this? Because our electric potential is not zero at any point. Okay, so best answer is B. Also, again, note too symmetrical. So that's it, guys. I don't have anything else. Let me know if you have any questions, and have, as usual, a really great day.